Okay, so this is video number 2. We're talking about how a muscle cell works, but specifically, what's all this nonsense about the nervous system communicating with the muscular system? So let's say that I'm playing some video games, and I don't know, I'm kind of tired tonight, so I'm really thinking about possibly pulling out a couple of games and playing them tonight myself. So when I go to put in a different button combo for whatever game I'm playing, I'm going to send signals from my central nervous system, which my brain is part of my central nervous system. I'm going to send signals, particular patterns, through my nerves, and they will leave my nerves, and those branches will be made up of these motor neurons. And they'll go through these axons of the motor neurons all the way to the terminal end of these axons. Now, this is where the action really gets going. That action potential reaches the end of, or the terminal end of the axon. And when it gets to the terminal end of that axon, it stimulates voltage gated channels on the terminal end to open and let calcium into the cell. Excuse me. Now, there's a lot of names for the terminal end of an axon. Some people call it a synaptic knob. Other people call it a synaptic button. Some people call it a terminal button. Whatever. It's the terminal end. It's the very end of the axon. And it looks like a little Hershey's kiss. And when that action potential gets down there, because of the stark change in the transmembrane potential, those channels open and calcium floods in. Now, the reason why it's important that calcium comes in at this moment is the presence of calcium ions inside the terminal end stimulate the synaptic vesicles to now move to the very edge of the terminal ends and open and release the chemicals that they have inside. These chemicals are neurotransmitters. So what winds up happening is the neurotransmitters, in the case of talking about motor neurons and muscle fibers, the neurotransmitter that we're talking about is acetylcholine, which is commonly written as ACH in a lot of textbooks. So this acetylcholine is now released from the synaptic vesicles. They float across the synaptic cleft, which is a space in between. It's a space that's measured in micrometers. It's I think it's like 5 micrometers wide. The space between the terminal end of the motor neuron and the motor end plate surface of a muscle fiber. And the acetylcholine floats across the synaptic cleft, and then it binds to receptor sites on the motor end plate on the surface of the muscle fiber. The reason for all of this is because my motor neuron is basically trying to talk to any number of muscle fibers to tell them, hey, I need you to contract, right? We can't let an electrical signal go over, because if that were to occur, we would never be able to control this contraction process. It would happen without any chance of us, and I'm trying to think of the word for it, of regulating the contraction. We would lose the ability to regulate a contraction. So that moment that you really just wanted to you were laughing and you just wanted to tap your friend, you would really actually smack the heck out of them, looking like WWE SmackDown, because you wouldn't be able to control the power, the force of the muscle tissue. So we change this electrical communication into a chemical communication by switching from an action potential to a neurotransmitter, which is that acetylcholine. Then when acetylcholine binds to the ligand-gated channels that are on the surface of the motor end plate, those jokers open, they let sodium in, and now we create another action potential, but this time it's on the surface of the muscle fiber. So now we've gone from electrical communication to chemical communication back to electrical communication. And now we have this action potential that we like to refer to as a muscle impulse. It's still an action potential, but we call it a muscle impulse. So you'll know that we've now left the neuron and we are now on the surface of the muscle fiber. And that muscle fiber now allows that muscle impulse, the muscle action potential, to travel. Now, the difference here is that when we had the action potential on the motor neuron, the whole reason of having the action potential was to travel from one end of the axon to the other. We are trying to send a message. We're not trying to, the neuron doesn't get anything out of sending an action potential, right? It's just its job. So it's trying to get the action potential somewhere else. For the muscle fiber, it's a different story. When it creates its muscle impulse, its own version of an action potential, it actually needs to interact with this because it's not trying to talk to anybody else. It is the recipient of all of this stuff that's been going on. So this muscle impulse or this action potential of a muscle is allowed to not only go across the surface of the muscle fiber, but it also has these things called T-tubules, which allows that action potential to go down into the muscle fiber itself. The T-tubule is kind of like a manhole where it allows the action potential to get access to what's going on under the street. And when it goes down under the street, it stimulates a cascade of events to actually happen there. And so you end up with a cascade of events that's happening inside the muscle fiber. So at this point, the action potential goes down the T-tubules into the muscle fiber, and that's when it meets a series of other structures that are there. And that's when you start learning about myofibrils, which myofibrils are these bundle of protein fibers that are inside of the muscle fiber itself. And then you also learn about the sarcoplasmic reticulum. And when that action potential gets down there, it stimulates the sarcoplasmic reticulum to release calcium. Now, I can tell you this right now. Anybody who takes anatomy and physiology, if there's one thing you're going to learn by the time you get out of that class, is that calcium is stupidly important. Calcium is ridiculously important because there's something to learn about calcium in every other chapter in anatomy and physiology. And here we are again, finding out that calcium is released from the sarcoplasmic reticulum within a muscle fiber. And this calcium being released activates what's known as the sliding filament theory. And this is when we see the protein fibers within the myofibril that I was mentioning, they start interacting with one another. And the primary two, there's more than two. I know for your purists out there, I know there are more proteins than just these two that I'm about to name. But for the simplicity of understanding what's going on, we're just going to talk about actin and myosin. I'm just going to mention them. Actin and myosin are two of the most popular protein fibers within myofibrils. And so actin and myosin are known as myofilaments. Yeah, there's a whole lot of myos, and you're noticing that everything's getting smaller and smaller, right? We had a muscle, then we had a muscle fascicle, then we had muscle fibers, then we got down to myofibrils, and now we got myofilaments inside of that. And these myofilaments are actin and myosin. And the release of calcium by the sarcoplasmic reticulum allows actin and myosin to interact with one another. And when they interact with one another, they attach to one another, and then they drag one another together like an accordion. And it causes these bracketed sections of actin and myosin, known as sarcomeres, to come together and shorten. And when you cause the sarcomeres to shorten, then the myofibrils shorten. And when the myofibrils within the muscle fiber shorten, then the muscle fiber itself shortens. And when the muscle fiber shortens, then the muscle shortens. And when the muscle shortens, we refer to that as a contraction. And that's when you end up having the muscle pull something. So if this is a muscle that's attached to, I don't know, the ulna or the radius in my arm, then that muscle is going to pull the ulna and radius, which then creates a movement. This is what I love to refer to as the law of ludicrous. which states that when it moves, you move just like that. If you don't know what I'm talking about with Ludacris, the rap artist, then, go look it up. Whatever you do, if you're a kid, though, be careful. There's explicit lyrics in the song. So I don't want to get mad with any parents out there. But he had a song that in the chorus that said, when you move, when you move, I move, just like that. So that's the same thing here. When the muscle contracts, it pulls the tendon. When the tendon pulls, it moves the bone that it's attached to. And when the bone moves, you move, just like that. So backing all the way back to the microanatomy that we were referring to before, everything happening inside that cell, when the sarcomeres shorten because of the actin and myosin acting with one another, attaching to one another, dragging one another, and then everything becoming shorter, coming closer together, pressing together, the sarcomeres come together, they shorten, then that makes the myofibrils in the cell shorten and come together, which makes the muscle fiber come together and shorten, which causes the muscle to come together and shorten. And when that happens, the muscles pull and that moves the tendons. And when that moves the tendons move the bone that they're attached to. And when the bone moves, you move, just like that. And that is how you get the contraction. But you can't stay that way, right? The opposite of a contraction is relaxation. So now the muscle fibers have to relax so that you can reset and do this all over again. And in order to relax, it's pretty simple. We just go in reverse. Everything that happened to make the contraction, we end up doing the opposite. So the fact that we release the calcium to get things started with the myofilaments like actin and myosin, we now reabsorb the calcium out of the cytoplasmic space, or the sarcoplasm, as it's called in a muscle cell. We reabsorb the calcium. We pump the calcium out. Removing the calcium now allows actin and myosin to go back to their original position, which allows the sarcomeres to elongate and they relax. That causes the muscle fiber to relax. Meanwhile, we have enzymes in the synaptic cleft that actually break down acetylcholine, and they recycle half of the acetylcholine back into the motor neuron to reuse this to make a new neurotransmitter to use again on the next time. Meanwhile, the muscle fiber relaxes, and when the muscle fiber relaxes, the muscle relaxes, and when it relaxes, it causes the tendon to, instead of pull, it causes the tendon to relax and to let go. And then that lets the bone go, and then the joint goes back into its original position, and then you have relaxation. And that literally is the whole thing in a nutshell. Now, are there other details? Yes, there are. So if you want me to talk about those other details, leave some comments, comments in the stuff below. If you liked what you heard, please like this video, share this video with your classmates, and if you haven't already, please subscribe. We'll see you on the next time.